Okay, we are at section 7.4, work done by a varying force. Now, let's share the PowerPoint, and you'll see that the total work done for this displacement, now we're just looking at the little slice there. The work done for the displacement from xi to xf, x initial to x final, is approximately equal to the sum of the areas of all the rectangles. So basically, we're integrating. We're taking each different rectangle and adding them up. So the area of one is fx delta x. So the work done by the component fx for the varying force as the particle moves from xi to xf is exactly equal to the area under the curve. That is the key point for this section 7.4. The work done by a varying force is the area under the curve. But let's go ahead and go through the slide. So work equals fx delta x. We have all these delta x, x sub 1, x sub 2, x sub initial to x sub final. So the work is equal to each of these rectangles. So the limit as delta x approaches 0 is, in other words, as we make each of those delta x is smaller, it's the sum of that fx dx, and that ends up being the integral from x initial to x final of fx dx is the work done. So the work is equal to the integral of x initial to x final of fx dx. Now, you can look at it as a particle. If it's a particle, then it's in, if it's moving in the x direction, it's the integral of xi to x initial, x final of the sum of all the forces times the dx, the movement of the particle. If it's a general, if it's not just moving in the x direction, it's moving in several directions, then the sum of the work is equal to the integral of the sum of the forces times just dr. You know, dr might be in the x direction and the y direction. It may be moving. Now, if it's not if it's like a deformable system, like we were talking about the balloon, then you take the integral of f dot dr and you sum all of those integrals of f dot dr for a deformable system. Work done by a spring, and we're going to have a little, I think I showed you the demonstration of the Walter Fent spring here. That on the Walter Fent, it was going up and down. Here it's sliding back and forth. Work done by a spring. When x is positive, the stretch spring, the spring force is directed to the left. So the force is equal to minus kx, where k is the spring constant. So that if x is in this direction, the force is backward. So there's always a negative component to the when you have a spring. When the x is 0, the natural length of the spring force is 0. In other words, there's no force. When you push the force in the negative direction, when you push the block in the negative direction and compress the spring, then the spring is pushing back in the opposite direction. When x is negative, the spring force is directed to the right. The work done by the spring force on the block as it moves from minus x max to 0 is the area of the shaded triangle, 1/2 kx squared max. Again, the work done is the area under the curve. So the spring force is equal to minus kx. The k is the spring constant, and it'll be expressed in newtons per meter. And so x is expressed in meters, and it's a minus k because if you stretch the spring, the force is in the opposite direction. If you compress the spring, the force is in the opposite direction. That's what the negative indicates. So f of s equals f Fi, that's the F in the unit direction, so it's equal to minus kxi. Okay, the force Fs exerted by the spring performs work on the block as it moves to its final position. So the work is equal to integral of F dot dr is the integral of x initial to x final of minus kxi dot dxi, and you have the, as referencing the graph before, you have from x minus x max to 0, the integral of minus x max to 0 is minus kx dx, and you end up with 1/2 kx squared max. So the integral of x to the n dx is x to the n plus 1 divided by n plus 1. So here the integral of x to the 1 dx is x squared over 2. So the work of the spring is equal to 1/2 kx squared with x max. 1/2 kx max squared. All right, so the work done by the spring force on the block as it moves from minus x max to 0 is the area of the shaded triangle, 1/2 kx squared max. And we go through this again, the work, the integral from x initial to x final of minus kx dx is equal to 1/2 kx initial squared minus 1/2 kx final squared. Okay, the force exerted by the spring performs work on the block as it moves to its final position. So the applied force is F applied I equals minus F Fs, F of the string, which is minus kxi, so it's just kxi. So the work is equal to F applied dot dr, which is the integral from x initial to x final of kxi times dxi. So that's the integral from minus x max to 0 of kx dx. And again, we have minus 1/2 kx max squared. And so the work is equal to the integral from xi to xf of kx dx equals 1/2 kx final squared minus 1/2 kx initial squared. Okay, let's take a quick quiz. A dart is inserted into a spring-loaded dart gun by pushing the spring in by a distance x. For the next loading, the spring is compressed by distance 2x. How much work is required to load the second dart compared with that required to the first dart? Well, you remember the 1/2 kx squared. If you double the x, so it's 2x squared, 2x quantity squared, so that ends up with 4x squared. So you end up with 4 times as much work is required to load the second dart. Okay, we'll stop there, and next we'll discuss section 7.5, the kinetic energy and the work kinetic energy theorem.